The new way we understand space is relatively similar to a pool. The objects in it move the space, or in this case, water around. Take a ball for example, it displaces the surrounding water to make room for itself, or a sponge, it pulls the water in, increasing its own size slightly. This is why, if you were to watch an object fall towards a black hole, it would seem to slow down the closer it came to the event horizon. Before it reached that point, it would seem to freeze entirely, slowly begin to turn red, and disappear. The light takes longer and longer to reach your eyes as the pull of gravity gets stronger, until a point where the light won't come to reach your eyes at all. It'll be pulled into the black hole and you will never have got to see what happened. Let's say you were the one falling towards the black hole. The closer you came as you fell towards it, the faster everything else would seem to move, as if looking into the future, although, this wouldn't do you any good, as you're falling into a black hole. Now, in this scenario, you may be interested in knowing, could you survive a black hole? The simple answer is no, but also yes. If the black hole is small, then it would warp you around its own curvature. Which, while being painful, is not the worst of it. You'd then be quickly pulled into the black hole and hit the singularity before you even realized what's happening. While, with a larger black hole, the pull may be stronger, the curving effect of its gravitational field is so small that you wouldn't notice, and, up until you cross through the event horizon, you could still escape the black hole. Before we go on, let's clear up one common misconception of black holes. Black holes do not suck things in, like a vacuum. To put this in perspective, take our own solar system for example. If the Sun were to be replaced with a black hole of equal mass, which is exactly one solar mass, not much would change for us at all, or any of the other planets. In fact, they'd retain their normal orbits. This is if you ignore the fact that our planet would become a freezing ball of death. Our idea of space being vast and empty nothingness isn't quite correct. Since the Big Bang, virtual particles have constantly been appearing into existence, and as quickly as they came, they're gone. One particle and one antiparticle, the moment they appear in our universe. They collide with each other as if they'd never existed. This happens throughout all space. Throw black holes into the mix and we've got Hawking radiation, first theorized by Stephen Hawking. When this process occurs right at the edge of a black hole, one particle gets sucked in while the other gets flung out into space from the absence of its partner's pull. This makes black holes slowly evaporate, radiating part of their mass away. But hold on 1 minute, it can't be that simple. As it turns out, it isn't. It would take 10,000 billion years for a black hole to lose even 0.0000001% of their mass. Many black holes have been around since the beginning of the universe. Many will also be among the last of anything existing in the universe. By the time the last black hole evaporates, the last star would have long since been dead. Well, what happens when black holes evaporate? A white hole? But that's another story.